In this lesson, we'll talk about the derivative and the tangent line problem. In the first section, we looked at an example of calculating the slope of the tangent line by looking at, say, the tangent line at 1. What we did was we took points like 1.1, 1.01, 1.001, and so on. And for each of these points, we calculated the slope of the line between those points. The goal was to look for a trend in the graph. This probably sounds pretty familiar. Now that we've got the concept of a limit, we could talk about this problem a little bit more closely. Let's start out by looking at the picture. In this picture, we've got this point C here. So you could think of C as 1 if you'd like. The first point is just at 1. And for the second point, you can think of this delta x as the increment that we're going. So say for 1.1, delta x would be just 0.1. For 1.01, delta x would be 0.01. We're just picking values of delta x. We're really getting them closer and closer to 0. What this makes is this point, which is really like maybe your 1.1, is c plus delta x. It's the point where you're at plus the increment. And the y-coordinate comes from just plugging this in to the function. Then we've got the rise here. The y-coordinates are f of c plus delta x and f of c. Then we simply subtract these to get the y change. And by the way, the letter delta x and delta y, we usually bring these as change in a variable's quantity. With that said, the slope is rise over run. Now normally we have a formula for that, but we actually have these concepts that we called delta y and delta x. So in particular, delta y is c plus delta x minus f of c divided by delta x. That is the slope of this secant line just in terms of this delta x concept. Let's go a little bit further. All we have to do is take the limit as delta x approaches 0. If we continue to get these values closer and closer to 0 for delta x, then the increment disappears and we really do have a tangent line. So from the left, we can look at delta x as kind of far away. Then we get a little closer, and eventually just taking the limit, we get this tangent line. From the right, you can start off with a kind of large value for delta x and shrink it to get closer, and as you continue this process, you end up also with the tangent line. So both sides make sense here, which is important for a limit. Let's continue and see what this looks like as a function. The slope of this tangent line that we just calculated is something we're going to want a lot more than what we're doing right now. This is what we actually call the derivative. It's one of the most important things in calculus. If you've heard the term derivative before, you've probably heard of a little bit of calculus. It is a very common thing. The derivative is this formula, which should look very familiar. This is the same formula for the slope that I was using a minute ago, but I'm using just any x instead of that specific c. And all I took was the limit as delta x approaches 0. This is the formula for the derivative, and we often call this function f prime of x. Now there are other notations, but f prime of x is a very common one. As long as we get that limit, we get the derivative, and we get a function out of this. So the derivative of a function is another function. We'll do some examples and we'll learn some tricks and all kind of interesting things. But right now this is the formula that gives it to us. The only other thing to note is that the derivative is not just the slope of a tangent line. You can think of it as the instantaneous rate of change of the function. You can think of it as the direction that the function's moving at that very instant. And we'll see plenty of applications of these. We've got the concept of differentiation, which is just a term that we'll use if we're referring to the process of taking the derivative. So you will see a few different terms that you'll want to know are all meaning just derivative. Like I might say differentiate this function, which simply means take its derivative. A function is differentiable when its derivative exists at that point, and a function can also be differentiable on an interval when it's differentiable everywhere inside of it. Now we don't talk about differentiability on closed intervals right now, but we certainly are allowed to do those. Here's a few other notations. You can talk about f prime of x is one of your notations, and here's another one. This is what we call dy by dx. I don't normally read it dy over dx. It's normally read dy by dx. dy by dx, let me show you, comes from this formula. Remember, this was just called delta y. This was just a change in y. So if I call this delta y over delta x, then taking the limit is where we call dy over dx, kind of these minuscule increments. We just call it dy instead of delta y. It's an instantaneous change. Another notation is d by dx of the function, which you can see is kind of similar. This is what we call the differentiation operator. It's saying take the derivative of whatever is coming after. This one is also a form of the differentiation operator, but this is much less commonly used. I'm just including it here for reference. Let's use this definition to try to get some information about what a derivative is in particular. The first example is f of x equals 5x minus 8. Now we all know that to be a line with slope 5 and y-intercept negative 8. Let's use this formula. What I like to do for these is just do a few pieces first. F of x plus delta x is simply take the function, and wherever you see an x, we're going to plug in x plus delta x. X becomes x plus delta x. Then we get, next line is f of x plus delta x minus f of x. I like to go ahead and tackle the numerator on the side. I get 5x plus delta x minus 8 minus the function, which was 5x minus 8. Notice the parentheses I just put. That's important because you have to subtract the whole thing. So I get 5x plus 5 delta x minus 8 minus 5x plus 8. You'll notice some cancellation occurs here. And I'll give you a hint. If you do this cancellation and you do not get rid of all the terms that don't have delta x in them, you've done something wrong. You should always be able to cancel out all terms with no delta x's. So we just get 5 delta x. Here's our definition. F prime of x equals the limit as delta x approaches 0 of this value that we just got. The f of x plus delta x minus f of x was just simply 5 delta x over delta x. So there's your formula. You've got like this delta y over delta x. Here's why you should always have delta x's, because they cancel out. So I get the limit as delta x approaches 0 of 5, which we know to be 5. This probably should not be a big surprise because that's the slope of the line. Remember, the derivative is the slope of the tangent line. So in particular, if it's already a line, the tangent lines all have the same slope. So we should not be surprised. Next example. Now this one's a little bit harder because of the x squared. Let's just work our way through it carefully. G of x plus delta x is 3 times x plus delta x squared. Now notice what I did there. I saw the x squared, and so I replaced x with x plus delta x, and it's inside the square. Very important that everywhere you see an x, you replace it with x plus delta x. I'll go ahead and simplify this one before I move on. If I square this, I need to use FOIL. It's not just x squared plus delta x squared. And what I get when I FOIL it is x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x minus 7. So then g of x plus delta x minus g of x, the numerator now. Let's go ahead and simplify this in the process. Start with this part. 3x squared plus 6x delta x plus 3 delta x squared plus 2x plus 2 delta x minus 7 minus the original function. 3x squared plus 2x minus 7. Now the same cancellation occurs here. You could distribute the negative sign, but you've got 3x squared minus 3x squared, 2x minus 2x, negative 7 minus negative 7. So this turns out to be 6x delta x plus 3 times delta x squared plus 2 times delta x. Now this is again your check. Every term has delta x in it, which means you have not made a mistake. Probably. Again, if you ever get something that does not have a delta x in it, go back and look at what you did. This is the limit as delta x approaches 0 of what we just had here. 6x delta x plus 3 delta x squared plus 2 delta x all divided by delta x. And now the cancellation occurs, but I will warn you, cancel every term. Delta x cancels in all three to cancel with the bottom. You have to divide every term by delta x in order for this to work. We get the limit as delta x approaches 0 of 6x plus 3 delta x plus 2. If we take the limit, the delta x is right here and there's no delta x's elsewhere. So we get 6x plus 3 times 0, because simple substitution works now, plus 2, which is simply 6x plus 2. Now that one is probably not quite as obvious for you guys to see, but what it turns out is that the slope of the tangent line of this quadratic graph is a linear function. As the quadratic function x values get larger, the slope gets larger, which I think you can imagine by looking at the graph. Next idea is when a function is not differentiable. There's three types, and you want to definitely learn these. You lose differentiability when you have a sharp corner, some sort of turn in the graph that happens abruptly. What happens is that you've got a limit from the left side and a limit from the left side, and the slopes are different, so we don't know which one to put. A discontinuity in the graph also causes it not to be differentiable. And another one is a vertical tangent line. The reason being is the slope of a vertical tangent line would be infinity or perhaps negative infinity, depending on how you want to think about it. But either way, that limit does not exist. Let's look at the graph of absolute value of x. And remember, you've got sharp turns, discontinuities, and vertical tangent lines. There's definitely no discontinuities in here. There's definitely no vertical tangent lines, but there is a sharp turn at x equals 0. With that said, the function is not differentiable there, but it is everywhere else. Differentiable on negative infinity to 0, parentheses, union 0 to infinity. So again, you want to watch out for sharp turns, like this one, vertical tangent lines, like this one, and also discontinuities. Let's put this together. Find all the locations where the function's not differentiable. I'm just looking down this function for sharp turns, vertical tangent lines, and discontinuities. X equals negative 2 is definitely a discontinuity. But there's another one also. At 1, there's an infinite discontinuity, which by the way at negative 2 is removable. Let's continue on. Looks like everything's in the clear right here until we get to 4. At 4, the graph temporarily goes vertical. So that's another place where the function's not differentiable. Vertical tangent line. And that appears to be it. I don't really see any sharp turns in this graph, just the two discontinuities and the vertical tangent line. Next one. At x equals negative 4, there's your first example of a sharp turn. But I notice another one that I'm going to go ahead and mark here. At positive 4, there's another sharp turn. Again, sharp turns mean that the derivative does not exist. It's not differentiable. Just a quick example. From the left, it looks like the slope is coming down at negative 1. From the right, it looks like the slope is maybe negative 1/4. Because of that, those two slopes are different. Well, which do I pick for the derivative at 4? We can't. Let's see what else is going on here. There's a discontinuity at 0. So that's another one. And then finally, I see another vertical tangent line at x equals -2. Sharp turns, discontinuities, and vertical tangent lines break the derivative, and we have a way to calculate the derivative using that function and limit formula. In the next one, we'll talk about some shortcuts, but for right now, remember that the derivative is the slope of the tangent line and the instantaneous rate of change of the function.